Hi, everyone. And firstly, thank you very much for joining us today, wherever you are in the world. Um, this webinar is going to be focused on climate change and flood risk, and it's aptly titled Transforming the Actuarial Profession. And I think climate change is really interesting, actually, because it's having this impact not just on actuarial sciences, but elsewhere as well. And that influence is that climate change is really forcing actuaries to think like data scientists. And the reason for that is that climate change is really making the past unreliable as a kind of prediction of the future. So actuaries really are having to think like traditional scientists. Next slide, please. And I can think of nobody else really better suited to talk us through this than my PhD supervisor, somebody I've known for a long, long time now. One of the world's leading scientists focused on this topic. How do we understand flood risk? How do we build computer models to try and simulate its impact now and in the future? Um, this is really, as I've said, having a pretty profound impact actually on many, many sectors, and actuarial sciences is indeed one of them. Um, at the end, we're going to have a poll and also Q&A. So as Paul goes along, please do drop questions into the Q&A box at the bottom of your screen. And as I've said, there will be a poll as well. Next slide, please. But I will just give a quick overview of the content today and then hand over to Paul to walk us through it. But Paul will be talking about climate change and flood risk. Like, how is climate change impacting flood risk? Why is it impacting it? Why is this significant for actuaries? Like, why do we think actuarial scientists should care about this phenomenon? And then keyly, we're going to talk through the different tools that have been developed in recent years to try and understand this. And as I'm sure Paul will walk through, there really has been a revolution, really, in our ability to understand flood risk, particularly at large scales over the past few years. There are still huge uncertainties and difficulties in understanding what climate change looks like in the future, but we've really made some profound steps actually to providing a whole range of different industries with tools to enable them to make robust and accurate decisions. So with that, I will hand over to Paul and I will be back with you at the end. Over to you, Paul.
Fantastic. Andy, thank you very much. Thanks for the introduction. It's very kind. And thank you for everyone for joining in and listening. It's a pleasure to talk to everyone this afternoon. So I'm going to just walk you through firstly, a little bit about climate change and flooding, and then look at how we might use science to help deal with that. So let's have a look at the numbers to start off with. Global flood risk is a large and in some ways growing problem. If we look at the MDAT, the UN's Emergency Events Database, and we look at average flood impacts from 2003 to 2022, every year, around about 75 million people on average are affected. There's a large number of casualties every year and in a huge amount of monetary losses. Importantly, all of those things are subject to significant upward pressure due to climate change and population growth into the future. So we know that over the last 20 years, floods have been a significant problem. And we can also use a branch of science, meteorological science, called climate attribution, to look at how those events have changed over time, and particularly to look at how extremes have changed. So here's a very nice graphic from a paper by Daniel Swain, one of the leading experts in this area, that just explains how attribution studies work. So what we're doing here is we're comparing a present-day climate to a pre-industrial counterfactual. So we take some extreme event, we take the observations and model simulations of that in present day, and we wind that back to look at how that event might look with pre-industrial concentrations of greenhouse gas contributions. So by developing that counterfactual, we can then look at the extent to which climate might have played a role in exacerbating the severity or the scope of those events under present-day conditions. So let's have a look at an example of this for the European floods of 2021. Well, we can estimate based on historical data that this was round about a 1 in 500 year event. There's nearly 250 casualties and a total loss to insurers of 2.5 billion and a total loss all round of about 10 billion euros. When we run these attribution studies compared to a pre-industrial climate that's 1.2 degrees cooler than present day, what we see is that one-day summer rainfall under 2021 conditions is somewhere between 3 and 19% higher than it would have been under pre-industrial. And this event was between 1.2 and 9 times more likely under the present day climate than it would have been in the far past. So climate attribution is an important and powerful tool of letting us know the extent to which current events that we're experiencing now are different to how they would have been in the past. And also, at the same time, socioeconomic pressures are changing, and the population at risk of extreme events is changing as well. So here's a really nice example by Kostas Andriadis of the University of Massachusetts. And this is looking at the annual time series of global urban area that sits in what is defined as floodplain in the Fathom numerical models. And you can see how this has grown over time, normalized by the 2015 total. And you can look at how different areas of land affected by different return period floods has changed. And this is indicative of the urban areas expanding, so also is the population. And we know something from climate models about how things will change into the future. Again, there's a lovely paper by Milley from 2008, which has become really classic in hydrology, called Stationarity is Dead. And these plots from the IPCC Assessment Report 6 clearly make that clear. So here you see global temperature change, land precipitation, September Arctic sea ice, and global mean sea level under different climate scenarios over time through the 21st century. And you can see here, I mean, I'm sure you all know are now familiar with these shared socioeconomic pathways and relative concentration pathways. But basically, the numbers go from the smaller numbers are lower emissions, and the higher numbers are more emissions. SSP 1, 1.9 or 2.6, that's probably a best case scenario under the Paris Agreement target. So if we meet all our commitments made at COP26, we implement all the net zero pledges around the globe, that is probably our best case scenario for climate trajectory. At the other end of the scale, our plausible worst case scenario is probably SSP 5, 8.5. And that's a significant acceleration from where we are now. And current trajectory is somewhere in between those two extremes. So we know that things are going to change into the future. And you can even see these very low confidence tails, which might come up with some rather extreme amounts of sea level rise if we get, for example, instability of the major ice sheets. And again, we know a lot about, or we have some projections about how population might change over time. And it's not just the absolute population. We also know that people are migrating, they're aging, they're urbanizing, and therefore we're getting concentrations of risk in ways that we haven't seen before and in places where we have not seen before. So you put all those things together. We know that present day climate is different to the past. We know that population in the floodplain has changed over the last 30 years. We have a fair idea that those trends are going to continue and even accelerate into the future. And it's no surprise that we find that flood risks are increasing, and that causes uncontrolled outcomes, principally for insurers, but also for asset managers and investment firms. This is some data from Swiss Re's reporting, and based on their analysis, we see that around about a third of the world's population is exposed to some sort of flooding. We've seen 30% increases in insured losses, and over the last 30 years, we've seen about a 1.2 trillion in global economic loss. And here's a breakdown of those statistics. You can see the insured losses by decade, not broken down by year until we get into the 2010s. But there you can see that the losses have almost doubled. And the last year for which data were available, when we compiled this figure, 2021, shows that the 2020s are looking to continue this trend that we've seen so far. But flood models, our ability to identify and therefore mitigate and hedge those risks, have lagged significantly behind this quite rapidly changing risk landscape. A really good example here is the Thai 2011 floods, and in terms of exemplifying an unmodeled loss. who knew? Well, and actually, we could have known that this was a problem. But at the time, insurers didn't take into account the fact that they had large liabilities to Japanese semiconductor firms, which had situated their manufacturing in the floodplains of the Chao Phraya River around Thailand's capital, Bangkok. When the event did happen and these industrial states flooded, the business interruption for the semiconductor industry was huge. And that loss blew back both first to Asian semiconductor firms and then back into global insurance markets. At the end of the day, this was a $47 billion economic loss, of which 18 billion of those losses were insured. And you can think of this as a market failure. There is nearly 30 billion of economic losses that could have been hedged through proper insurance and yet weren't. So that's the situation as we best understand it at the present time. But why, and the purpose of listening to this seminar is, why should actuaries take notice of all this? Well, I mean, the very obvious fact, as Andy has alluded to, is that the past does not equal the future. And therefore, using historical averages and assuming those are stationary is not going to be a good strategy going forward. In fact, what we've seen with attribution studies is the past is not even a good guide to the present day. The risk or extreme event climate of 2025 is very different to the risk climate in the historical averages of extreme events. So if we just do a simple statistical model of the losses we might expect in the present day, it's almost inevitably going to be wrong. And that means that even for insurers who have a classically short-term view of risk, even insurers are impacted by this. We typically write insurance contracts no more than 12 months ahead. We're thinking about how much reinsurance cover or how much losses can I expect next year. And as a consequence, insurers haven't historically needed to worry so much about climate change. But because the past is not even a great guide to present day, even insurers' short-term views are impacted. And if we think about the market for actuarial services, there's an awful lot of different clients who we might be able to provide advice to who want long-term views of risk. If you are thinking, for example, of the performance of investment portfolios over time, threats to infrastructure. If you're building a port or you're siting a solar power farm, or you might very likely want to know how that investment or that asset is going to be impacted by climate change over its lifetime, which may be decades or even towards the end of the century. We might want to know about supply chain risks, aka the Thailand example, because that can be extremely damaging and difficult to spot a priori. Our regulators might want us to undertake stress testing to make sure that portfolios are robust to climate scenarios. And we might have to undertake regulatory compliance, where we have to demonstrate our understanding of all these modeled risks. And the point we're trying to make is that this might be rather different to the classical model of actuarial work. And all of this, of course, is going to need data. And a good question becomes, therefore, where is that data going to come from? And really, how should we treat it? Well, in terms of flooding, actually, we can do quite a lot. We've spent many years, many decades, building numerical computer models that can do the thing that we see on the right-hand side of the screen. So this is a computer simulation of the Carlisle floods of 2005. Carlisle is a small town in northwestern UK. It was experienced around about a 1 in 100, 1 in 150 year event in 2005, which overwhelmed the local flood defences and caused about £500 million of loss. So a modest size event. Carlisle's a relatively small market town, but still it's £500 million of losses. So it's non-trivial. And we have developed over time as scientists ability to solve physics-based equations that conserve mass and momentum, that can simulate water propagation over complex topography. And secondly, we've developed the data sources in order to drive these models. So you can see here that we've got a really detailed representation of the terrain of the city, and we're actually here resolving individual buildings in the terrain data. And we get this as a result of remote sensing technologies, in this case, airborne laser scanning. But there are many new data sets that have been developed over the last couple of decades that allow us to conduct these really detailed local modeling studies. And these things work in, they're relatively intuitively simple to understand. I mean, if you had a bit of coding ability, we could probably sit down and knock up a simple version of one of these codes in an afternoon, and they're not that tricky. And conceptually, they're easy to understand as well. We spread water over a grid with a topography, conserving mass and momentum as we go. So here you can see how a particular simple 5x5 grid model would evolve. So if we start off at time 1 with water in the middle cell, obviously it's a fluid dynamical problem. Fluids can't resist forces and remain at rest. So that water can't just sit there in a column if there's nothing there to bound it, and it must flow into the adjacent cells. We can compute those fluxes based on Newtonian mechanics. And we also know that if water flows out of the middle cell and into its neighbours, the amount of water that flows out must balance with the decreasing water level in the centre cell must balance with the increasing water level in the adjacent neighbours. Simple conservation of mass. It can't be created or destroyed. And then if we step through time, we can move that water in sensible, physically realistic, mass conservative, momentum conserving ways over complex topography. And that, in essence, is what the animation that I've just showed actually does. So in terms of creating these models, they're relatively parsimonious. They don't need a great deal of information, but that information needs to be high resolution and high quality. So we'd start out, most importantly, with some terrain data, which these days, in the best case, we get from airborne laser mapping. We'll need to know what's happening below the water surface as well. So we'll also need to know the channel bathymetry, because even during big floods, a lot of the water is still going down the river channels because that's where the water is moving most quickly. So we need the bathymetry. We'll need some boundary conditions, so how much water is coming into our model. And we'll need some kind of hydraulic engine to do the mass and momentum conserving computations. And here, within our group, we use a model called ListFlood FP, which my university research team have developed over the last 20 years. But other models are available, and because they solve physics-based equations, if you set them up in the same ways, they will often give you a similar result. And if you do that, voila, here they are. So we produce a prediction of inundation extent and water depths, and we can compare that to satellite and air photograph images of the flood to see how well we are doing. And the answer, and then we have some quantitative ways of comparing those flood extents and water levels to our observations. So just as a slight digression, because it helps explain the next two slides, for flood extent, we use this critical success index, which looks at the intersection of and union of the modelled wet and the observed wet areas. The nice thing about this metric is very robust. It ignores all the areas where the model says things are dry and the observations agree, because those are really easy to predict. Typically, your flood is a small proportion of a rectangular domain. So if you had a model that said there was no water there at all, you'd probably get quite a good result. So we ignore area A here, and we just build our metrics over areas B, C, and D. So that's called the critical success index, and we use it for pattern matching. And then for water depths, we can use mean absolute error or RMSE, just as you might expect. And the answer to how well can we do with these local models, the answer is really quite well indeed. So this is a case from the UK from November 2000, where there were really big floods. And for floods over the River Severn, the UK Military Defence Research Agency flew an experimental airborne radar system that's normally used for submarine hunting in the North Atlantic. We weren't allowed to know exactly how this radar worked. We know it's an X-band radar with particular polarization. But we managed, after much negotiation, to get hold of these data and use them to map the floods. We then built a numerical model of these floods and compared the two together. And here we see we had 4 of these radar scenes where you see a dashed vertical line in the panel on the upper right. And this is how well we're doing. Light blue is correctly predicted, red and yellow are over and under prediction. Dark blue is outside the radar swath, so we know nothing about that. And we're getting a match here to the observations of around about 90% from our model. This is fantastic. I mean, most environmental models that predict spatial patterns do not do this well. Think about the simulations of rainfall that you see on the television news broadcasts every night for tomorrow. Those have very, very sketchy spatial patterns which don't turn out to be that correct. Here we're getting predictions of inundation extent almost down to pixel level. Here's another example. The first example was rural. This is how well we do over urban areas. This is a later event on the Severn, Tewkesbury in 2007. Here you see the dark green muddy floodwater and it's surrounding Tewkesbury Abbey. I don't know if you can see my cursor, but you can see Tewkesbury Abbey here. And we built a model of this flood, fed it with the observed flows, the really high resolution terrain. And if we pull out the model prediction at the time this photograph was taken, this is what we get. I'll just toggle backwards and forwards so you can feast in the glory of this result. In fact, what I would suggest is just pick an area of the shoreline and focus on it as I toggle backwards and forwards. And you can see that the prediction of the shoreline is almost spot on. This building here in the air photograph is clearly on a little promontory and is high and dry. And that's exactly what the model says would happen. So these models were in local scales where we've got really good data work exceptionally well. Here's an oblique photograph of the same flood with Tewkesbury Abbey surrounding. You can see from this, though, the problem in scaling up. We can do a really good job when we have time and effort and great data, but all flooding is local. The difference between success and disaster might be a few tens of meters. The difference between a house being completely wiped out and it being safe could be a few meters difference in vertical elevation and a few tens of meters in space. So our models have to have high fidelity. They require high resolution to work. And we have a challenge, therefore, in going from these local models, which we as scientists know that we can build, to the kinds of models that insurers and investment houses, banks will want from us, which are continental to global scale. Risk is mutualized at national scales in insurance. And therefore, we need to provide data, high quality, high resolution data at a commensurate scale. But over the last 10 to 15 years, we have spent a huge amount of time looking at how we do that, and going from local to global. So now we can combine global terrain data sets, global estimates of where river channels are, statistical models that define extremes. We can deploy the compute power and have the efficient algorithms to solve those hydrodynamic equations at high resolution, a few tens of meters at global scales. And most importantly, we built all the automation tools that allow us to do that, because clearly you can't do this process manually. And so therefore, global flood modeling since about 2015 has been a rapidly emerging paradigm. And this is where Fathom's been working to try and develop better and better versions of these codes. And you can see our progress from version 1 in 2015, where Andy and Chris Sampson, his colleague, built our first model, to the latest version in 2024. And we've gone from 1 kilometer resolution now down to 30-meter resolution. And if I say that every halving of the grid resolution is an order of magnitude more compute cost, then the leap from 1 kilometer to 30 is absolutely huge. That's orders and orders of magnitude more compute that we have to deploy to do this. And you can see, whilst we're not testing the skill here, you can see that intuitively the later models, they pass a sniff test. They're looking more and more realistically like real floods with better terrain data. And you don't have to just take my word for that. We can look at the validation data. So we can look at those CSI and water level error statistics. And we've done so over a variety of test cases globally. We've taken national and regional engineering maps and satellite images and post-event reconstructions. And then maps of post-event high water marks, and we've compared them, our models together. And we can see as we move from up through the versions, a real improvement in the skill of these. And you can see, for example, CSI. I mean, my general rule is if you can get the CSI above 0.7, you have a pretty skillful model. The very best cases I showed earlier on had a CSI of 0.9. And I've simulated once or twice places where we've been able to achieve that level of data, of model accuracy, because we've got high quality data. But version 3 of the Fathom model, CSIs of 0.75, we're getting 75% of the active floodplain correctly predicted, and root mean squared errors under a meter when global terrain, this is within global terrain model errors. This is approaching what we can do for a typically good local model. So yeah, upper limit for good data is probably these numbers, and we're kind of approaching that at global scales, which is astounding. More recently, we've been adding climate dynamics to this whole process. So we've been taking global and regional circulation models and their predictions of things like precipitation, temperature, and coastal sea level. And then we've been running those through extreme rainfall and hydrological models and ocean models to look at changes in different flood drivers over time. And by developing that into an interpolation framework, we've got a way now of going from a set of scenario projections to being able to interpolate to any climate scenario, any flood peril, anywhere in the world. And we do that through a series of change factors. So we look at the extent to which, in the future, under particular climate scenarios and particular ensembles of climate models, what's the change factor for an extreme, in this case, precipitation, by particular time horizons into the future. So this is from the for precipitation, we use something called high-res MIP, the high-resolution model intercomparison project. And you can see the scaling factor for extreme rainfall under a particular climate scenario by a particular point in the future. I think this is RCP 4.5 by 2100. And you can see here that in most places of the world, extreme rainfall goes up according to this ensemble of climate models. But in some places it goes down. And in some places where we see the hatched line, we're uncertain about the sign of change. The models we have don't agree on the sign of change. So this gives us great information to both inform how climate might change in the future and also the amount of trust we should put in those projections. Rainfall's not too bad. Changing river flow is a much more uncertain picture, and therefore our knowledge about how river flows might change in the future is more sketchy. Here we see that there are it's more balanced which areas see increasing river flows and which areas see reductions. And that's because of the complex interaction between temperature and precipitation. We might get more precipitation into the future, but sometimes that's going to fall on dry soils and therefore might not generate the same flood response. And you can also see here there's much more hatching. So in many places, our models don't agree on the sign of change. But nevertheless, this is our current best view. It's correctly weighting and characterizing the strength of the science, and we can use that uncertainty in our decision-making process. Coastal change as well, same kind of thing. This is now absolute changes in mean sea level. Most places go up. Actually, though, in some places close to the poles, because they're so close to the major ice sheets, actually you see reductions in sea level rise because of glacial isostatic adjustment. And what we can do here is simulations like this. This is Houston in 2020, the area at risk of a 1 in 100-year coastal flood event. And this in red is the extra land at risk by 2050 from the same event. And using these, we can use this information to help people take a whole series of different decisions about managing their risks. Put all that together and we can form a view of how flood hazards change into the future and what we know about the uncertainty in those. So here I plot the change in global flood hazard under low and high climate scenarios. So this is our plausible best case and plausible worst case, plus uncertainty bands for total at the top, and also broken down into the different drivers from fluvial, pluvial, and coastal. Coastal we're most certain about, pluvial more uncertain, fluvial most uncertain at all. The shading here represents the likely 60% range based on climatological uncertainty. So what you can see is that the scenario really matters for flood, but it's going to be quite a way past the 2050s before we can conclusively tell from the flood hazard which of these trajectories we're on. So we're going to have to deal with decision making under uncertainty in all these cases. Summary, this is just the numerical summary of those data. So we'll take a quick look at those and move on. You can see that, hit the Paris Agreement targets, median change is within 10%, easily manageable, less than climatological uncertainty. So, dealing better with the risk we face in the present day should actually deal with an awful lot of that problem. SSP5, plausible worst case, increases of flood risk of flood hazard of 50% will be much more difficult to adapt to. So, and then lastly, what I've been talking about so far has been flood event mapping or flood hazard mapping. These maps show what gets wet where, but it doesn't tell you what gets wet at the same time. Maps are static and they show you a flood depth for a given return period event. And actually, often what we want to do in insurance is show spatially correlated financial losses. And to do that, instead of these static flood hazard maps by return period, where the intensity of the event is constant everywhere, we need to generate synthetic events which have a realistic spatial footprint. And therefore, we develop metrics such as average annual losses and loss exceedance probability curves. And the way we do that, from moving from hazard to risk, is we create statistically, we create a set of spatially realistic events which show the intensity of the event varying in space in a realistic way. We take that and use that to sample from our hazard layers, which show then the physical intensity, the water depths for each location for each event. We then link that with exposure data, which tells us about where assets are, and then something about the vulnerability of those the vulnerability of those assets were the flood event to happen. And last, we can build all that into a financial module that takes into account things like deductibles and other factors to look at the financial losses. And this is what is known as a catastrophe risk model. They're quite difficult to build, but nevertheless, they are extremely powerful in looking just beyond average annual losses until the full probability loss exceedance curve. And these things allow you to quantify financial risk across lots of different perils and understand drivers of risk accumulation for particular portfolios. In science terms, we've been able to use these to do really quite cool things as well. So here's a paper we did in 2023, where we built one of these models for UK flood risk, and we looked at its ability to replicate the observed flood losses from the Association of British Insurers. So the dashed vertical line in the middle of the histogram is the average ABI annual flood loss from 1998 to 2018. And that's an observed expected annual damage of around about £700 million. That sits very nicely in the histogram of our modelled loss distribution. The ABI data is over 20 years. So here we've simulated 10,000 years of CAT model, and we've sampled 10,000 random 20-year samples from that CAT model to compare to past estimates. So you can see that our model, the average center point of our distribution, our model EAD sits very close to our observed expected annual damage. And the green histogram gives us some idea of the climatology of 20-year loss totals given current climates. You can also see the loss estimates that we get from the Environment Agency's National Flood Risk Analysis and the UK's Climate Change Risk Assessment version 3. You can see that these lie way outside of our modelled loss distribution and quite away from the observed losses. So CAT models are a way of more robustly getting at loss distributions, their climatological variability, and how those might affect different portfolios. building up from very granular data into these aggregate totals. And then in this paper as well, we were able to look at the loss exceedance curves, a standard insurance industry metric, and how these changed over time with different climate forcings. So here we are in 1990, around about 0.6 of a degree of warming above pre-industrial. And actually, as we move to 2020, extra half degree of warming, but actually very little difference in flood loss exceedance curve. And that's also true if we get to the Paris Agreement targets, which is the blue line, which I stupidly haven't labeled. But this is the 1.8 degree line is what we get to as in terms of peak global warming if we hit the Paris Agreement targets. And also meet all our net zero pledges. If we only meet the COP26 emissions pledges, the NDAs, the National Declared Contributions, or the NDCs, National Declared Contributions, if we only meet those and we don't follow a net warming pathway, a net zero pathway in the countries that have promised that, here is where we get to. Now we're starting to really bend this loss exceedance curve. And if we miss our carbon reduction targets and the climate sensitivity turns out to be higher than we think, here's where we end up with. If we get global warming above pre-industrial up to 3 degrees or above, now actually we're looking at really quite big increases in 1 in 100-year UK annual flood losses. And I should emphasize as well, these are the national totals. There's a geography to this which underpins all of this. And even if we hit the Paris Agreement targets and net zero pledges, actually there's still going to be significant winners or losers because of that underlying geography of risk that comes from the really granular flood model that we've got. So to summarize my point here, the take home here and my thoughts are that increasingly actuaries need to be able to make use of and manage these data. Using information from numerical models like those I build and machine learning models that others do. And essentially start to become data scientists in addition to their actuarial skills. And that involves quite a change in mindset and involves acquiring some new knowledge. Risk has changed already, and it's going to change further into the future. And therefore, I think there's great value in using forward-looking models to provide clients with more robust advice. In terms of floods, which is kind of really the only thing I know about, recent numerical and data developments are really strongly transforming our ability to do this risk assessment under conditions of non-stationarity. And actuaries actually play a really key role in the adoption and use of these emerging tools. So, if your boards or the people you advise want information, it's you they go to, not me. So actually, it'll be actuaries who are spearheading the use and adoption of these emerging tools in the insurance and other sectors. And you've got the power to drive real change in how organizations do their risk analysis and management. But a caveat, a warning, models are complex and their outputs are uncertain. If you're going to use these, you need to really carefully understand their strengths and weaknesses, and also the limits to prediction. It wouldn't be a bad idea to hire 1 or 2 climate scientists who can help you do this. Even if you don't do that, I think there are things you can do to protect yourself. One of those, very importantly, and I would say this because I'm a scientist, is to insist on transparency and independent peer review of the models that you use. If somebody is telling you that they've got a machine learning or artificial intelligence model that will solve all your problems and has got brilliant skill, and they won't tell you how that works, I'd be very, very cautious about accepting it. Black boxes, where you're not allowed to know what's under the hood, you have to be deeply suspicious about. And with that, I hope that's been interesting and informative, and I'll hand back to Andy to just finish off the seminar. Andy, back over to you.
Thanks, Paul. That was an awful lot of information, so hopefully everybody enjoyed Paul's talk. One thing I didn't point out at the start, we do actually have a white paper. It's available in the chat. It's called a primer for actuaries, so please do download it. I can confirm it's extremely interesting and has even more information relevant to actuaries. We do have a bunch of questions that I'm going to go through as well. I think a poll will also be coming your way in the chat as well. Maybe I'll kick off with the first question and I'll hand it over to Paul. The first question, actually, it's a few questions. What is the input to your model? Is it water volume, precipitation intensity, or river discharge? And this kind of alludes to your last comment, actually, Paul. What is the performance of your hydraulic engine compared to other AI models? Paul, can I hand that over to you?
Sure. So the boundary conditions, the inputs to this model are either extreme rainfalls, extreme river flows, or extreme coastal water levels. So depending on the type of flood we're simulating, we'll select a different type of driver. So it will be spatially varied, time varied rainfall, or it'll be river flows in different catchments or water levels along the coast. And we get those data from river, rain, and coastal water level gauges. But because those don't exist everywhere, we take them into statistical models and we regionalize them so we can predict extreme river flows, for example, everywhere on the global river network. And that's classic hydrology. It's a regionalized frequency analysis. It's old school. It goes back about 50 or so years. It underpins a whole bunch of classical engineering tools in hydrology. The only tweak that we have is that finding those relationships, we find correlations between extremes and things that we can measure, catchment characteristics. The only thing that we've changed recently is we now use machine learning to find those relationships rather than, least squares regression and best knowledge. How do the skill of our models compare to AI models? Well, it's very important to say ours is not an AI model. This is physics-based conservation of mass, conservation of momentum. We use a bit of AI and machine learning to create the input data sets. But after that, it's Newtonian physics that's controlling it. And it's expensive to solve and robust. It's a personal view, and I've given talks at Google flood risk workshops on this. But I think for flood inundation prediction, AI is the wrong approach to take. I mean, machine learning and AI models work best where we have lots of labeled training data. And floods, by their very nature, are rare. We have very few observations, and the observations that we do have are quite poor in places. So a lot of the data is disinformative. So as a consequence, I don't think there's enough information out there to really properly train IA models to emulate what flood inundation models do. We can probably train them within sample. So normally what people do instead of training on real data, they train their AI on a model. So it can be no better than the numerical model that you built in the first place. So first of all, just use the numerical model and that will be better. Secondly, there's a lot of effort to training an AI models, which is hidden, and that's hidden cost of development. Again, just build a proper numerical model, which has got all that information in. And then lastly, AI models work well within sample, and they don't predict out of sample very well. The further you're away from where you've trained them, the less well they do. And for floods, we're always interested in things that we've never seen in the historical record, or are bigger than anything we've modeled or observed in the past, or will change in the future with climate change. So, my advice at the moment, and I'm happy to be proved wrong, and it'd be quite cool to be proved wrong, but I don't think AI models are going to help with this particular problem. But it's a personal view. It's probably quite an extreme one, but there you go.
Thanks, Paul. That was as complete and full an answer as I would have expected from you. So thanks. I think the next question in some ways might even be more profound. And I know you and I could probably do a whole webinar just on this topic. But the question is, how confident are you in the reliability of global climate models for different scenarios?
Yeah, good question. I think taking an ensemble of models and looking where they don't agree on the sign, even on the sign of change, is a good start. They have skill at predicting certain things in terms of global mean temperatures, anything close to the mean, anything at large scales. But as you drill in to finer spatial scales and to the more extremes of the distribution, their skill tends to fall apart. So their precipitation predictions, in particular, are not as good as they could be because the grid scales of those models are so large that they don't capture physical processes like convection that we know to be really important for extreme rainfalls. Nevertheless, I think whilst they may struggle with absolute uh, uh, predictions, I think their estimates of, in many cases, their estimates of the direction of change and the magnitude of change are a lot better. And therefore, that's what we use. But yeah, we do take it with a pinch of salt. We do weight by the uncertainty, and we do put uncertainty bounds on our future projections. And all of those things, I think, are the scientifically honest thing to do. So it's a qualified yes. But again, all models are wrong. Some models are useful.
That kind of leads us nicely on to the next question, which I might have a crack at answering, Paul. And that is, to which return period do the fluvial change factors correspond to? I suspect the magnitude and sometimes even the sign of change to be heavily dependent on the return period. This actually is quite relevant for what Paul has just described, because fundamentally, climate models, especially the global ones, don't really give us the information that we as risk modelers need. And as Paul mentioned, I'm talking here about spatial scale, but also about the tail ends of distributions. Like we just don't have that many years of simulation. So when it comes to actually providing estimates of future flooding and future return periods, we actually have to provide quite generalized answers with regards to how return periods, for example, would change. And what I mean by that is that we principally apply single change factors to all return periods. So we amplify or indeed decrease magnitudes for all return periods universally for different scenarios. And the reason that we do that is that we just don't have enough years of simulation to differentiate how those things might change in time. So that's just one example of how we have to try and get some useful information from climate models, and that can be some quite generalized answers or signals for change, and try and apply them to the kinds of data sets that we at Fathom produce. So it is at the moment, truthfully, not ideal, and we have to come up with these methods to try and do that.
Yeah, I think that's a good answer. I mean, I would also, the only thing I would add is that in climate model runs, we've obviously got many more smaller extreme events than really, really extreme events. So we tend to bias, I think, towards the more observable extremes, or the extremes that are more observable in the climate model outputs that we use. It might be that the most extreme events have a completely different physics mechanism to the smaller ones. And we're not really accounting for that yet. Climate models haven't got the fidelity and the skill to really let us dig into that problem in the way that we would ideally like.
Yeah, I mean, and if I could just add one more point, one thing I think we can say for sure is that at Fathom we might be trying to produce what we think are some of the most robust ways of answering these questions right now, but for sure the answers will change in time as the models evolve, and we've seen this with some models that we're using in the UK where we have kind of next generation climate models. For sure, the answers will change in time. As the models evolve, they will tell us different things about what the future looks like, particularly when you start to represent some of the physics around things like convective rainfall in more robust ways. So, and unfortunately, we're definitely not converging yet on an answer for these things. A simpler question for you, Paul. What are the main sources of uncertainty in these models?
So actually, if you'd asked me that question 20 years ago, I'd have said terrain data, but particularly at global scales, but even here in the UK. But over time, that error has been beaten down. Airborne laser altimetry has really given us fantastic DEMs over many developed countries, and even in sort of like big sparse countries like America, the amount of lidar data that's been collected is really going through the roof. But at the same time, global terrain data sets really had no skill 20 years ago, and now they're really quite good. And a lot of our effort over time has been developing new terrain data sets. So that error has significantly reduced. And I think it's one of those, what's the current limiting factor problems? You beat down one error and another one becomes the largest in the stack. And I think our largest error at the moment is probably the boundary condition. So what's the magnitude of extreme river flows, extreme rainfalls, and coastal water levels? And that's problematic because that's difficult because we don't have rain and river gauges everywhere that we would like. The global river gauging network is pretty sparse. It's densest in countries that have got lots of money to spend on it. And places like Africa, we're almost completely operating with very little information. So I think boundary conditions is our current biggest uncertainty. I think channel bathymetry, there's no satellite technology at present, and none in the foreseeable future that can measure the shape of river channels underneath the water surface. So that has to be estimated. That is currently a problem, but there we have a new satellite data set called SWOT, which measures water surface elevation. Although that's not the bed, actually, once you've measured lots of water elevation dynamics, there's only so many bathymetric shapes that can feasibly exist that would recreate the observations that you have of the water level. So actually with SWOT, we're going to be able to beat down that particular uncertainty quite a lot more than we have at the moment. So yeah, used to be terrain, now it's boundary conditions. Bathymetry is currently a problem, but that's one area where we can beat that. And as we said previously, climate change factors, again, not ideal as well. That is for future projections. That's possibly our primary uncertainty there.
Great, thanks, Paul. And I've just scrolled down and seen there's actually a lot more questions than I'd realized. So we'll try and get through them. I don't think we're going to get through them all. So if we don't, please do follow up and we'll get back to you. I would like to leave a couple of minutes at the end as well to just talk through some of the products that we have here at Fathom so you can understand exactly how you can use the tools and technology that we have. So this is a great question. On the CSI index you mentioned, how do you determine the proper return period of the observed event to compare against the modeled event? That's a great question, and I know one that Paul will love answering. So, Paul.
Yeah. So normally, and in those two local cases in the UK, we had river gauge locations where they had measured the discharge to at least some degree of accuracy during the event. And those were gauges where we had very long, multi-decadal runs of historic data. So we could produce an extreme frequency analysis and estimate the return period of those events. When we go to validating our models globally, say we get a satellite image in a location where we do not have ground gauges, it's really tricky to know how big that event was. Plus, return period is not constant in space, as we've alluded to. And then when we're validating a satellite image over a very large area, it's not the same return period everywhere. And we know that, but we're quite tricky to know exactly what that is. So in some places, we can do a really good job with that. In other places, it's a problem.
Thanks, Paul. Another question. I might answer this one just because I'm glad somebody's asked it. Why does flood modeling seem so advanced while for other hazards we're still lagging behind? Well, I'm glad you say that because actually I would say that's the opposite to where we were 10 years ago. Like 10 to 15 years ago, flood really was the peril that lagged behind everything else. The spatial complexities, as much as anything, really meant that we just couldn't represent it very well at all. So that's maybe testament to largely Paul's work, the work here at Fathom, but work from our colleagues around the world. So I actually, flood has traditionally lagged behind other perils, but maybe I just don't have enough knowledge of how other perils are modeled. But certainly a few years ago, flood was lagging behind others.
I mean, two things there. I mean, flood's difficult because it's also local, but it is an area where satellites over the last couple of decades have really given us the data sets to really knock back on some of those errors. So yeah, that's why we've seen a lot of progress.
How do you consider the flood defense system impact? So how do we represent defenses in these models?
Oh, fantastic question. So the answer is that in places like the UK and the US, there are databases of where flood defences are and what their standard of protection is. Those are still not complete. The US Army Corps of Engineers reckons the US National Levee database only is about 30% complete. So what we do is we have to model where we think flood defences are. There are some global flood defense databases which give the standard of protection at country level. And we also have done lots of work in identifying flood defences in very high resolution terrain data where we have it. So we have some ways of modelling what we think the flood defences should be and where they should be located based on ancillary information. It's a very imperfect science. What we could do is a really good labeled data set of flood defences and their standard of protection that we could start to machine learn the hell out of in order to be able to do this better. Lots of great colleagues looking at this around the globe at the moment. There's some promising results, but there's no real great solution, and therefore we fall back on this paradigm for places where we know nothing and where we don't have high resolution terrain data. We model it from country scale estimates based on local ancillary data.
Wonderful. We've got time for one more question. I will say, Paul, if you can, it's a good question, but if you can, keep the answer brief because I would like to wrap up very quickly with a summary of our products. This is another great question, so thanks to everyone for some really great questions. I'm really interested in when we move from hazard to risk. You mentioned we need to use synthetic event set instead of taking return periods. How do we build synthetic event sets, and why use them and not return periods? So why a return period is not appropriate?
Well, it's because if you look at a real event, our hazard maps cover the whole of a country or the whole of the globe with a single return period. And if you look at a real flood event, it doesn't look like that. So a flood event hits London and it doesn't hit Yorkshire. And therefore, our hazard map, which shows a single return period everywhere, is wrong. So we have to build these synthetic footprints of events, and we do that based on river gauge data, and it's essentially cross correlation. What's the probability, given a gauge in the network, a location in the network is extreme, what's the probability that all the other locations in the network are extreme at the same time? And by developing those matrices of correlations and sampling from those, we can statistically, synthetically generate event sets.
That was a very concise answer to a complex question, so thanks, Paul. We will get back to your other questions. I'll wrap up just by saying that Fathom has the most comprehensive coverage, actually, of any modeling group in the world when it comes to flood hazard data. So our flood maps cover the whole planet for any flood peril. That's river flooding, flash flooding, coastal flooding, anywhere in the world. The model fidelity and accuracy varies. In some territories, we have higher resolution data sets where the input data allows it. Places like the US, the UK, Japan, we have high resolution models. And keyly, these data cover all climate scenarios. So via Fathom's API, you can send locations and get answers for any climate scenario that you want, actually, out to 2100. And this functionality is also wrapped up into our CAT model. Our CAT model gives you financial losses. It's globally consistent, so you can plug in global portfolios, again, for any type of flood hazard, all major asset types covered, and get a real understanding of your potential financial exposure for the whole planet. And keyly, this is also now being developed under any climate scenario as well. So I would say that this is the most comprehensive tool for understanding global exposure and global risk. And also, crucially, we provide a really comprehensive understanding of uncertainty in these models as well. And hopefully from Paul's talk, you've got a good understanding that when it comes to understanding flood risk, particularly under climate change, the uncertainties can be huge. So you really do need that comprehensive understanding as well. So with that, we're at the hour and we'll wrap up. And I'll say again, thank you very much. Thanks, Paul, for a really great talk. And we'll follow up to the questions that we didn't get to. But again, thank you, everyone. Have a good day wherever you are.